The continuous random variable that you're likely to encounter most frequently is called the normal or Gaussian probability distribution. And we say that a random variable, we'll call it x, is distributed normally with a mean of mu and a standard deviation of sigma if you can represent its probability distribution using the function f of x over here on the left. And if you were to do that and draw that out on the normal line, you would get a bell-shaped type curve like you can see in the lower right-hand corner of the screen. There's a special type of the normal probability distribution that we're going to be using frequently, and it's called the standard normal probability distribution. And it takes place when we set our mu equal to 0 and our standard deviation, or sigma, equal to 1. And we call that random variable z, so we say z is distributed normally with a mean of 0 and a standard deviation of 1. And then our z value is then distributed using the standard normal probability distribution. Given a random variable, x, which is distributed normally with a mean of mu and a standard deviation of sigma, we can find the probability that that value, x, is between the points a and b using integration. So we just take the integral from a to b of a probability density function, f of x dx. And what this probability density function is doing is it's finding the area under our normal distribution or bell-shaped curve from, we'll say a down here, up to b. And this area is then just the actual probability that x is between those 2 points, a and b. Now you're probably thinking to yourself, this is a non-calculus based course. How are we actually supposed to find the area under the curve from between 2 different points? And the way that we're going to do that is through the use of tables. Now if we wanted to create a table for each mu and sigma combination, there'd be an infinite number of tables because there's an infinite number of mu's and sigmas. However, we have a shortcut. We can convert any mu and sigma, normally distributed variable, down to our standard normal distribution using our z-score formula that we discussed in a previous video. So our z-score formula converted our value, x, by subtracting mu and dividing by our standard deviation, sigma. And this is essentially converting our variable, x, which is distributed normally with a mean of mu and a standard deviation of sigma, into a standard normal variable, z, which is distributed, again, normally with a mean of 0 and a standard deviation of 1. This means, since we have this formula, that we can just create a single table which has all of the different regions for z for several points, and then we can use that z table to look up the probability that our variable z, so probability that a is less than z is less than b, and then those values will be the same that it would be for x with the different standard deviation and mean. There are a couple types of z-tables that you may come across in your career, but the z-table that we have on our screen here and the z-table that we have in our book both try to find the area under the curve from our mean, 0, all the way up to whatever the z-score is that we're looking for. So we'll try to find up to the z-score of 1.23, which means we're looking for the probability that our z value is between 0 and 1.23. So the way that we find that value is we go over to our z-table and we look down the left column until we find our 1.2, which is right here. And then we go along the top row and we find our plus 0.03. So this is giving us our 1.2 plus 0.03, which is giving us our 1.23 value. So we just follow those lines down. So we follow 1.3 and 1.2 until they come to our value here of 0.39065, which means from 0 up through 1.23, we have the probability of 0.39065, or 39.065% chance that a standard normally distributed value falls between 0 and 1.23. So since this is pretty important, we're going to try a couple of different examples. So for our second example, we're going to use our mean is equal to 3, and our standard deviation is equal to 2. And then we're going to try to find the probability that our x value is between 1 and 4. So to do that, since our z table here is finding the area under the curve from 0 up to 1 standard deviation, we need to find our z-scores for here. So we're going to find our z-score of 1, which is 1 minus 3, divided by our standard deviation of 2, which is equal to negative 2 over 2, which gives us negative 1. And then our z-score of 4, which is 4 minus 3 over 2, which gives us 1 over 2, which gives us 0.5. So we just need to find our two z-scores. We're going to look for negative 1. Well, we don't have a negative 1 here on our side, but since our bell curve is symmetric, meaning that the area under the curve from the mean up to 1 is the same as the area under the curve from the mean down to negative 1, we can just use that z-score of 1 to find that area under the curve from our negative 1 up to 0. So in that case, it's just this value here, 0.34134, excuse me. And then we just need to find our area under the curve from our mean up to 0.5, which is just this 0.19146. And we just need to add those values together because our probability of 1 less than x less than 4 is equal to probability that negative 1 less than z less than 0.5, and that's equal to probability that negative 1 is less than z, which is less than our mean of 0, plus the probability that 0 is less than z is less than our 0.5, which we just found our values out to be of 0.34134 plus 0.19146. So we just add those two values together, and that will give us our total area from 1 to 4 with our mean of 3 and our standard deviation of 2. So for our next example, let's try to find the probability that x is between 7 and 9.5 if x is distributed normally with a mean of 6 and a standard deviation of 2. So first, we're going to find our z-scores for 7 and 9.5. So we have 7 minus 6 divided by 2 is equal to 1 over 2 is equal to 0.5. And then we have our 9.5 minus 6 over 2, which is equal to 3.5 over 2, which is equal to 1.5 plus 0.25, so 1.75. So since both of our z-scores here are above 0, so we have 0.5 and 1.75, and our z-table is finding the probability that x falls between 0 and whatever our z-score is, we just need to find the probability that x falls between 0 and 1.75, and then just simply subtract the probability that x falls between 0 and 0.5. So we'll find our probability that 0.5 is less than z is less than 1.75, which is the same as our original probability question, and that's equal to the probability that 0 less than z less than 1.75 minus the probability that 0 is less than z is less than 0.5. So we just need to find those two values on our z-table. So we'll go 0 to 1.75. So we find our 1.75, we find 1.7, we find 5, we find out where they meet, which is right here, of 0.45994. So we have 0.45994. And then we subtract off our z of 0.5. So we have right here, which is equal to 0.19146. So if we just subtract these two numbers, we'll get the probability that our x value is between 7 and 9.5, given that x is distributed normally with a mean of 6 and a standard deviation of 2.